This seminar today will mix few fields because I understood it's a nano seminar. I know that many people here will have more focused questions. You're welcome to ask, either in the middle or at the end or after the talk, whatever you feel comfortable with. Okay, so this is where we are located, the Nano building of in BIU University. I'm starting with thanking all the funding agencies. Most of the work I will show you today is carried out for the BIU 5 years energy storage consortium, that I'm the Israeli lead of this consortium, and also worked under the Israel Science Foundation funding. This is the work I'm covering today. And we have some extra funding for other activities that I will maybe mention today if we have enough time. The most important thing is to thank my group. I will also end by thanking them, but if we don't have time, so most of the work done by them. I'm just typing. So our lab focus is designing artificial and functional interfaces. We are dealing with various applications. We have design of surface films that are selective on surface of any substrate you can think of. So we did it on glass, activated carbon surface, making a blind surface into a rectangular one. We have also worked on biofilm protection of catheters, but most of the work in my lab is on energy storage materials. We are protecting materials that go through degradation as active materials in batteries, and this is what I will focus on today. So the content of my talk, I will start with introduction to atomic and molecular layer deposition. It will be a short introduction, but I think it's very useful. I will show you how we step forward the synthesis approach and process approach of atomic and molecular layer deposition. I will demonstrate the importance of the film protection as protecting film on active material that go through degradation processes inside electrochemical active environments. I will show you some analysis methodologies we developed in my lab for inoperando mass spectrometry studies of the efficacy of these protection layers in battery application. And I think I will show also some new active material, and I will give a background on rocking chair battery for people that are not from the community. So a brief introduction to atomic and molecular layer deposition. So we all know that if I take trimethyl aluminum as an example, react it with water, I will have alumina and methane as a living gas. Chemical vapor deposition, took it a step forward. Together inside a reactor, when I have a substrate that I want to deposit the alumina on, I can flow together the trimethyl aluminum, let's call it the blue reactant, and the red as water. If I'm flowing them together into a same environment, I will have co-deposition of the aluminum oxide and then living group of methane. This is the chemical vapor deposition. Atomic layer deposition is taking it even a step further. There is an alternating sequence of these two reactants, meaning fast bulbs here on the blue, fast bulbs here on the red, and then they are entering the reactor separately. We are separating, and by the amount of alternating, the number of alternating sequences, this is going to determine the thickness of the deposited layer. A short cartoon to demonstrate that. You can see that the surface is terminated with hydroxides. This is trimethyl aluminum as an example, getting into the reactor, reacting with the hydroxide on the surface, and living group as methane. Now, when there is no room for further reaction, the trimethyl aluminum is leaving, and we are cleaning the reactor. Putting with water. Water again will abstract the methyl group and the methane, and this is the way to go by atom. It's a very simple cartoon, very nice. We all hope it really works, but it doesn't. But it enables deposition on high aspect ratio substrates. Yes, on high aspect ratio substrates, and we are doing it also on powders. I will show you later on. What we are trying to do in my lab is not stopping at two components elements. So this is a binary alumina or titania or vanadium oxide, but we are adding, instead of having two precursors, there is one way to increase the complexity, the composition of the thin films. Maybe I lays it out. We are enriching the composition of the thin film by adding just more precursors. I will give you one example from my postdoc and then the beginning of my book. This is a way to add more elements and control the desired functionality of the thin film. So, for example, if you want to deposit ion conductive for lithium ion, this is a name of family of materials which is composed of lithium, phosphorus, oxygen, and nitrogen. We are starting with the development of lithium oxide by lithium tetrodoxide and ozone or water, and then adding into the trimethyl phosphate to also embed into the film phosphorus. And then with nitrogen plasma, we were capable of developing glycol as a lithium ion conductive thin film. Later, we demonstrated here this process. It's a four-step process. We demonstrated it also on active material in my group. This is in collaboration with Dr. Michal Estes from the Weizmann Institute. So this is a thin film deposited on active material. We control the thickness, it's 30 nanometers in this example, but we needed 4 steps with this process. This is a process from a postdoc. And one of the goals we put in my lab is we keep the fundamental of the chemistry, but we are trying to make this process more scalable. So this is an example how we took it a step further. This is an atomic layer deposition of the sister system of a napon. We are doing the same also with lipon. Instead of using a nitrogen plasma as the source, we are using the nitrogen here in the precursor, and then it's only a 2-step precursor. We pre-treat the surface with ozone, and then we are capable of depositing on the active material thin film of napon surface. This is still unpublished, but as you can see now, we are preparing it for publication, which is kind of obvious. We are developing the process with 2 steps instead of 4 steps for sodium ion conductive on active material. This is how the setup looks like. We have, not sure that the pixel here allows you to see, but here we have ELSA connected to a glove box. ELSA is capable of deposition of sulfide base, so highly reactive thin films that cannot meet moisture. This is why it is connected to a glove box. It also enables us to coat on reactive metal surfaces, so we can coat on lithium or sodium without exposing to moisture. The sister Anna is outside the glove box, and Anna is capable of also of plasma deposition. So we have here plasma unit connected, enriching also the available precursors for our thin films. These are 6 precursors and 2 more oxidation or reducing agents that we can put in. We can follow the deposition or the growth rate of our thin films using QCM inside our reactor. And we can also coat powder. Most of the work that I'm going to show you today is based on coating over powder, active material that is active in battery. Before we spread it or before we prepare the battery, we are coating the material with the desired thin films that will mitigate the degradation pathways of these active materials. I did not choose the names. This is my daughter. I even have photos when it came. It was a very happy day when the reactors arrived. Okay, so this is how the tumbler looks like. It's a custom-made tumbler inside the reactor. So when this oldest version, we have now stainless steel or based versions, but it is rotating, and inside this tumbler we can put powder of whatever type we want. And of course, this is active when the reaction takes place. This is closed. And you can see the nozzle here entering the tumbler and then go to the powder. These are a few examples: alumina over silicon powders. This is just a process of aluminum oxide I spoke about before. This is a process I will elaborate a little more later, because this is a single precursor process. We're just laying on the fact that we have loses oxygen on the surface of the active material. This is active material for batteries in collaboration with BASF. These are lithium vanadium oxyphosphates on over carbon nanotubes that we are capable of deposition conformally, even on very challenging topographies of powders. This coating I will also elaborate more later on. It's a lithium silicate developed in my lab as a process on high energy cathode material. This is the sister process. Instead of using water and trimethyl aluminum, we are using the ethylene glycol. And you can imagine the cartoon before. Now, instead of having just oxygen and on the top of the oxygen I have aluminum and oxygen. We also have the residuals from the organic group. So we just abstraction of the hydrogen here will take place, methane will leave, and we will have a molecular layer deposition rather than atomic layer deposition. We are also demonstrating the same with hydroquinone, and we have also a system with amino acids. This is in collaboration with Professor Idan Hod from the Lyon University, where we are drawing MOFs on the surface of carbon fibers. And this is a recent work from my group when we are developing, based on nicotinic acid, we are developing biofilm repulsion thin films in collaboration with the group of Professor Banin from Bar-Ilan University. So I'm going to show you today a few approaches we are doing in my lab for atomic layer deposition. One, which is basically atomic surface reduction, self-limiting process with only a single precursor. And I will also speak on a multi-atom deposition from a single precursor, meaning in a single precursor, we can now put few elements of choice, just to have short process with the desired functionality and composition. So I showed you before this cartoon, what we are doing now, we are using just a single precursor and still have a very conformal thin film. I'll show you how it works. So we call it atomic surface reduction because the reactants like the zinc or like trimethyl aluminum are highly reactive on oxygen-rich substrates. And if there is a transition metal involved, they will reduce the transition metal near the surface. This is why we call it atomic surface reduction. And then we can achieve conformal coating without the need of oxidizing agents, just a single precursor. This is a scheme that my student put together before we had a calculation, and this is published. Maybe it's the first work that is completely new from my lab. Few years back, trimethyl aluminum on the surface of oxide cathode material. This is a very complex oxide of nickel, mangan, and cobalt. And on the surface of the nickel, mangan, and cobalt, we only purged trimethyl aluminum. We then went to our collaborator in Serbia National Laboratory, Dr. Kevin Gahan, to really check if this is a spontaneous reaction, if it can take place on the surface of oxide material without the need of oxidizing agent. And it turns out, well, he chose lithium cobalt oxide because all the other oxides are not stable thermodynamically. So he was limited in terms of calculation for his DFT. So the lithium nickel oxide or lithium manganese oxide, they are not stable thermodynamically. He chose LCO, and he took the most reactive surface and then moved to the less reactive surface. Yet in both of them, there is a spontaneous decomposition of trimethyl aluminum on the surface of the LCO. So if we have lithium cobalt oxide, and we purge trimethyl aluminum on the surface of the oxide, there will be attachment to the surface, abstraction of the methyl group that will then move to another oxygen, and it will be spontaneous reaction. And this is what we also showed with XPS, that the movement of the methyl group and the presence of the reducing agent, that's trimethyl aluminum or diethyl zinc later on, I will show you, if there is a slight reduction of the transition metal that is close to the surface. And when we try to publish it in the first publication, then we had issues with the reviewer. He was arguing if it is really take place, if there is really reduction of the manganese. But later, as a follow-up work, we were very happy to see that the group of Jesriela and Grilli, they published later a very detailed mechanism of the reaction of the transition metal next to the surface with a very, very similar oxide, where there is a clear cascade of reaction that takes place on the surface, reduction of the transition metal. In this case, they calculated the manganese, exactly like we showed with the XPS, that there is a reduction of the transition metal close to the surface by the presence of trimethyl aluminum or diethyl. And this is what we observe in the TEM after the process. You can see that there is a very thin film. It's a self-limiting reaction. We have 3 nanometers. If we close the light again, is it obvious for you? Yeah, so there is a 3 nanometer thick thin layer on the surface of the oxide, covering the entire surface. And when, it doesn't matter if we purge even further, this is 50 pulses. of trimethyl aluminum. And if we pulse further, it does not go any further at this temperature, meaning that this is a self-limiting reaction. So the only way to really answer this question is to invest a lot of time in TEM for billions of particles. This is a small portion of, so the way this particle looks like, you have a sphere of maybe 3 to 5 microns, and this sphere is really composed of small crystallites. And when we look on the crystallites, we couldn't find a crystal that is not coated. I cannot say that based on that all of them are coated. I can just say that we looked on many and they are not, but there are gazillions. Okay, so they are coated. One more thing I can tell you that if I'm now changing parameters, and I will show you later with diatism, I'll keep this question, because what we can follow the suppression of the transition metal signal in XPS. If I'm doing that and with time it disappears, then it means it's a full coverage. So the next process that we are developing, and we will come back to this one later on, just instead of using 3 precursors for 3 elements, we are using 2. And in the green one, we just a priori synthesize a precursor that will contain both elements of interest. So it can contain lithium and silicon, for example. We are now capable of doing lithium, silicon, and zinc in a single precursor of molecular layer deposition. This is in collaboration with Professor Yitzhak Kaloel from the Technion. And the analysis of the surface, or the capability to really see what's going on a 3 nanometer scale, is done in the dynamic nuclear polarization solid state NMR at the group of Dr. Michales in the Weizmann Institute. So what we proposed is a thin coating which contains 2 or 3 elements of interest in a single precursor. So now we are capable of taking precursors from the family of sililithium, but instead of only sililithium, there is also zinc, and that was inserted synthetically before the reaction inside. And this is a single precursor together with ozone. We are capable of coating with film that contains all the elements of interest. So instead of having 4 to 6 steps reaction, we have only 2 steps reaction. This is highly important for industry application. It is already patented, so it's in physics now. This is the first example where we took only sililithium with ozone and reacted on the surface of active material. We have deposited lithium silicate, and we can control the amount of lithium inside by controlling the amount of lithium in the mother molecule. This is the capability. This is the strength of the group of Professor Kaloel, what they can do. And I will show you later on how it helps the electrochemistry, because now I've shown you so far that we are capable of developing thin film with desired composition and processes. But why is it interesting for us? So, short introduction to all each of us, and then we will go back to see why it is important. So, these 3 important people, and they are the Nobel laureate of 2019. So, generally speaking, he did it for the cathodes that really works, and he did it for the anode that really works, and also for important finding on the cathodes. I will explain now what cathode, anode, and electrolyte really means. So if we have 2 phases, one blue and one green, okay, keeping it simple. I don't know chemistry or materials to sit here in the audience, but let's say that this phase really wants to give electron to this phase, meaning really he wants to reduce it. So this one will be the donor, and the other one will be the acceptor. If I'm putting them together in contact, there will be a spontaneous, highly exothermic reaction of injections of electrons from the blue phase into the green phase. And in order to compensate on charge, there will also be movement of cations. So electrons will move, and the cations will also move. This is highly spontaneous exothermic reaction. In battery, we don't want it to happen. In fact, most of the hazardous or the unwanted reactions inside the battery, it's goes through thermal runaway, or what you see as explosion of battery, is when these 2 phases come in contact. We want to separate these 2 phases. So what we did, we separated them with electronically insulating phase, which is still ionic conductive. this is a phase that allows the movement of cations, but suppress or block completely the movement of electrons. And now if you put a wire from one side, from one phase, from the blue one to the green one, the electrons can flow, and then there will be a reduction. And to compensate on the charge of the electrons, there will be movement of cations. And this is how the battery works. So this is the side we call anode, this is the side we call cathode, and in the middle, this is the electrolyte. And when we discharge the battery, electron flows, cations also flows, and then the cations move from one phase to the other phase, and this is when the battery is fully discharged. Now, if we want to charge the battery, we just need to go on the reverse reaction, just plug it into electricity, and the ions can go from one side to another. This is why it is called rocking chair. It's like rocking chair of the ions from one side to the other. The issue of the interface is highly important because, for example, in your cell phones, graphite, which is the anode, is highly unstable. Thermodynamically, it shouldn't work. But it is kinetically stabilized by the fact that there is a very thin surface, which is solid electrolyte on the surface of the graphite, and it stabilizes the graphite to suppress further reduction of the electrolyte solution, because the electrolyte is also reacting over here. On the cathode side, and this is what I'm going to show you today, there is also a reaction which is oxidation of the electrolyte solution. So this is this phase when we are charging the battery, it goes to high potentials, and then it can oxidize the electrolyte solution. So what is interesting that in fact in Israel we have the most common or accepted model for the surface of the anode side, and it is called the solid electrolyte interface. It is first reported and explained by Professor Manuel Pellet from Tel Aviv University, and in fact this is cited as one in the scientific background of the Nobel Prize of 2019 as one of the most important and cited papers in the field, because it really explained the model why graphite is stable in electrolyte solution where it should not be thermodynamically stable, meaning there should be a reduction of the electrolyte solution from the graphite. But he showed that this phase is formed and then electrons are blocked, but ion can really move through this solid electrolyte interface. It's really inspiring the community to stabilize active material inside battery even before closing the cells. So this is really the approach we are taking. So if we are looking at a battery, this is a rocking chair battery, we have the anode side that hosts the ions, and we have the cathode side that also hosts cations, and they are just replacing cations as we cycle the battery. And in the middle, there is movement of cations in the electrolyte solution. So really how to choose active materials? How to choose active materials for batteries? We want to have anode that is capable of hosting as many cations as possible. The amount of cation hosted in the anode will determine the energy density in the battery. And same goes for the cathode side. Distance is voltage is how much the anode, the donor, want to inject electrons to the acceptor. The more it wants to thermodynamically wants to inject electrons, then the voltage will be higher. And the higher the voltage, the higher the energy of the battery. The more ions can go into the anode or into the cathode, the higher the capacity. Here it is in values of milliamp hour per gram. But it is really translation of how many ions can go into the hosting material. So the more the capacity, the more the energy. So it seems like if I'm going with what we currently have, we have graphite. Let's just change it to lithium, and we will have higher energy density, or let's change it to silicon. If today we have lithium cobalt oxide in most of your cell phones, or lithium iron phosphate, let's change it to these oxides. Very easy. Why not to do so? Okay, so we can just conjugate oxygen as your cathode, lithium as your anode, and Daniel mentioned that we had worked together about these systems because they are very promising in terms of energy density. Why not doing so? Or we can just take lithium with one of these oxides. We have lithium. Let's close the battery based on this material. Well, the truth is that this diagram doesn't tell you the entire truth. So it just gives you material of choice, but it is not telling you the challenges on the surface and the challenges that are dictated by the kinetics of motion. So the mobility of the lithium in some of these phases is highly slow, so it's very sluggish. You can't use it. Electrolyte instability on the surfaces is also an issue. And electrodegradation pathways are also a challenge. So in fact, when we look inside the battery, it's not as simple as this cartoon but there are many complex reactions. It's more like this. So the interface of the cathode is highly reactive with the electrolyte solution, especially when we go to high voltage cathodes, meaning to cathode they really want to be reduced. And if we are going to negative electrodes with negative anodes, they are also reducing the electrolyte solution. And many of these processes is interfacial related, many of the degradation processes of the materials. One example of how we really can improve the surface or the energy density is because silicon, when you react silicon with lithium, there is an alloying reaction. When you take graphite, it is interstitial diffusion of the lithium into the graphite. You maintain the gap. Also, it is a layered graphite. Lithium goes in, and the highest stoichiometry you will have is lithium to every 6 carbons. When you are dealing with silicon, it is an alloy reaction. So instead, you are not ending with silicon, you're ending with lithium-22 silicon 4. Okay. So this is why the capacity is very high. Yes. Yeah, so the amount of cations you can put in per gram of material is even higher for silicon when you're comparing it to metallic lithium because of density. The challenge, however, also related to the amount of silicon. The more you put, the more you are expanding your material. If I take a grain of silicon and lithiate it fully, the volume change is 300%. Okay, so and then when you are shrinking it back, it is cracked. Okay, and so you can imagine that many of the processes here are highly dependent on the entity or the composition of the active material. So this is a very good question, because here when I take lithium cobalt oxide, which is a common oxide used in your cell phone, the actual value for capacity is 150 milliamp hour per gram, meaning the amount of lithium I can put in is limited. If I take this oxide, it is a lithium and manganese rich nickel cobalt manganese oxide, we can demonstrate in lab almost twice the value of lithium cobalt oxide. We can do it, but the stability is highly limited because the voltage of operation is higher. One more thing, you can see that theoretically speaking, the amount or the capacity that should be exhibited with lithium cobalt oxide should also be almost twice the value that is now really operational in lithium cobalt oxide. It's also related to the voltage of operation. So one of the phases, lithium and manganese rich, is actually 2 phases together, one monoclinic lithium manganese oxide and a rhombohedral layer structure. It's a composite. It goes as a micron scale here, but many small crystals. And if I'm looking on, and now there will be some electrochemistry because there is no choice, but I'll try to simplify it. So when we take this phase, it is first lithiated. All these dots in between is lithium. Now, when I want to take the lithium out, meaning you take your battery and you charge it, you plug it into the electricity, and now you are biasing, you're forcing the voltage of the cathode to go positively. When you're doing so, lithium are leaving the cathode and going back into the anode. So I'm biasing positively the voltage, and this is the voltage measured on this material. And what's going on is lithium leaving the cathode, leaving the layered structure of the cathode, and the layered structure is now empty from lithium. And when we go higher in voltage, some parasitic reactions takes place. So not only lithium is going out, but also nickel might migrate and take position of lithium, creating more rock salt phases, therefore killing the battery. Because when I will then want to inject lithium back, it will be clogged. It cannot go in. More things that take place when we go to higher voltages, there is oxygen released from the oxide itself. Many oxygen on the surface are actually loose. They are not completely bonded to the surface, and there will be oxygen released, and the oxygen released will react with the organic solution, which is mostly alkyl carbonate solution. So there will be a release of not oxygen only as oxygen, but also as peroxide or peroxide species, and also as singlet oxygen, and they will react spontaneously with the organic solvent to form lithium carbonate on the surface, which is also undesirable. Yes. Oh, very nice. So I will give a short answer, and then so there are many approaches in the community. So for example, I have a collaboration with Oklahoma State. What he is capable of doing is really measuring the stress in operando. So he can really study the stress and strain of electrode materials. So we can really follow some physical properties. In my lab, I will show you later on, we are following in operando the mass spec using online electrochemical spec. And there are some attempts to do, sorry? Yes, we are following the phases using XRD, but the XRD will give me the answer about the phase. We are also doing in operando Raman. But if I really want to follow the evolution of gases, I'm using the mass spec. And there are also works with ambient pressure XPS. Also EPR. So basically everything, tomography, for sure, yes. So anything you can, so the field really, because there is a lot of funding in this field, and many national laboratories are involved also in the US. So there are heavy equipment that was really developed for this system. If I'll take an example, it's more politics of science or maybe history of science. So lithium oxygen, it inspired everyone because the high energy density of the system. But what it ended up to bring to the field is a lot of analytical tool that is capable of measuring in operando the processes. So this is a very good question. I will give one specific example from my lab later on. So what we are doing here, we are developing artificial cathode electrolyte interface, which is a derivative of the name solid electrolyte interface by Professor Peled. So we really coat this material. You want to see if coating will suppress the degradation of the active material. I showed you before that we have a very thin film on the surface of the cathode, and when we want to diagnose the evolution of gas in operando, we are using online electrochemical mass spec. This is how it is behaving in a real battery cell. The evolution of gases is really swelling the battery. There are species that can be from the electrolyte solution in the gaseous phase as CO2. There are also species that can come from the electrolyte itself. It's a lithium PF6 inside the battery cell, and we are following it using an OEMS cell. Inside the OEMS cells, we have everything. We have anode, we have cathode, we have electrolyte solution. And from the orifice of these cells, it is directly connected to online electrochemical mass spec. Okay, so we can follow the evolution of gases. This is an example from lithium oxygen cell. When we treated the surface, you can see the black one. These curves are the cycling of the battery, meaning discharge and charge, discharge and charge. And the dashed lines are the evolution of gases. So when it is protected in the black one, the nitrate treated surface of the carbon, you can see no evolution of gases. And when it is unprotected, you can see evolved CO2 as we cycle the battery. So what we have shown here two properties of this is not a work that I wanted to focus on today, but because you asked, you can see that the voltage is lower for the coated one. This is better. It means healthier oxygen reduction reaction, and it is also lower in voltage for oxygen evolution reaction. So both are improved. We improve the redox reaction of the oxygen, but we also suppress the evolution of gases, the undesirable gases. This is not coating. This is surface treatment with lithium nitrate. So it's a different thing. The coating I showed you before in a real battery cell, it's a thin film of the alumina on the surface of the high voltage cathode. And you can see here that CO2 for the treated one is suppressed. This is the cycling of the batteries. You can really follow that when we are going up, there is evolution of gases. It is highly suppressed when we are coating. Compared to the uncoated, there is also accumulation of CO2 over time. Same thing goes for the oxygen. So both are suppressed by the fact that we coated the active material. When we go to When we go to the electrochemistry, we can see that the capacity is also improved. This is about twice the capacity you have of lithium cobalt oxide in the commercial available battery. And you don't really need to understand all the electrochemistry, but I want you to remember here, this is 4C. 4C means how much current I have if I'm trying to discharge my battery 4 times in 1 hour. Very quickly. I'm trying to discharge my battery 4 times its capacity in 1 hour, meaning trying to fully discharge my battery in 60/4, okay, 15 minutes. And you can see that the coating actually suppresses the kinetics when we go to high rates. The coating of the specific alumina is in 2C, we do not see it. In 2C, it is less pronounced, but when you go to 4C, the untreated one is better than the treated one. And the reason why is because here, as we cycle the batteries, there is also evolution of surface film on the cathode anyway from the lithium carbonate. And at some point, the lithium carbonate will be better than the alumina. This is why we went and changed the surface film. And the way we are capable of following the surface of the cathode, can you see here the crack and the crack? So the uncoated one, if the gas is not evolved, if the gas is evolved, the battery is cracked over time. But when the gas is suppressed, the evolution of gas, because we do not see cracks. And again, if we take 2 SEM and we follow every particle, we didn't do it. We did not count thousands of particles, but we couldn't find significant cracking. And the cracking with the unprotected one was very easy to find. So this is after 100 cycles of the battery, meaning discharge 100 times and then go to a microscope and see if there is evolution of surface cracks. We then demonstrated the same thing instead of trimethyl aluminum. We were using diethyl zinc on the surface of the same active material. And again, we see a reduction of the transition metals on the surface. And when we follow the gas evolution, there is suppression of gas evolution when we are coating our material, and significantly improved long-term stability of the battery. This is the red one, is for the coated. It means for 100 cycles, we are cycling our battery, and we have a capacity retention of 93% comparing to significantly less. So this is about 81% capacity retention of the active material, which is not protected. One more thing, that here, even if we go to 4C, it is not a great surprise, but the zinc oxide should be a better lithium-ion conductive material from two different aspects. One is the lithium zincate itself is a better conductor, and the second one is that these are grains, and there is also more surface conductivity of the lithium ion. But when we are going to 4C here, we have 14% improvement by the coating of the zincate. What also we did with the surface treatment with the diethyl zinc is that when we went to different temperatures, we could find that it is very hard to find the zinc in the 150 and 200. So even though if we take the same process, purging just diethyl zinc on the surface of the oxide, we couldn't easily, it was very hard to detect the presence of zinc with XPS. But when we take it to ICP-MS, same amount of zinc is there. So there is obviously something that is happening with the zinc, which is related to the presence of zinc, but it is not only on the surface. So when we went to higher temperature, in fact, what happened, we have a Prof analysis and STM analysis. You can see that this is at 100 degrees. The zinc is located on the surface. But when we go to 200 process, the zinc is migrating into the active material itself. And it is actually doping this site in the lattice itself, and stabilization is even better when we are using 200 degrees. This is different oxide. It's nickel, cobalt, manganese, 811. It's not a facet name. It's just the concentration is 80% nickel, 10% cobalt, and 10% manganese. So this is the nickname of the. But you can see that the zinc penetration with 100 is maybe 10 nanometers deep, but when we go to 200, it is significantly deeper. And again, the electrochemistry is improved. This is 100 degrees surface coating, and the 200 is even better. This is another very important cathode material for next generation battery. and we can follow also the cracks. So this is the nickel cobalt manganese oxide before cycling. It's a sphere with many small crystals, as I said before. When you are cycling it, the crystal is completely cracked. You can see many cracks, and this is the coated one. And this is after cycling the coated. Significantly improved the maintenance of the morphology of the material. I'm going to skip to the next section, but we are also manipulating to put multiple elements in a single phase. The reason we are doing it is because we were interested in synthesis of lithium-ion conductive thin films based on silicate, because the thermodynamical stability at high voltages is promising for silicate, and our capability of putting lithium in will improve the kinetics. This is what we hoped, and this is also what we found. So instead of 3 precursors, we are using 2. Again, this is in a collaboration with the group of Professor Apeloy for synthesis, and the group of Dr. Michal Eskes for analysis. I will show you what her capabilities really brought to our understanding of the functionality of the thin film. This is the thin film that I showed you before, the lithium silicate. And it is coated again over the high energy lithium and manganese rich cobalt oxide. We could follow the position of the thin film using XPS, but when you look on the XPS, it was very hard for us to see what is the chemistry through the 3 nanometers, because we could see residual carbon. And it was interesting for us to see if there is a difference from the outer surface of this 3 nanometer thin film. How is it behaving close to the electrode, and what is the environment really far, like 3 nanometers far from the electrode? So it's very close. We couldn't detect it with any other tool, but Michal, she could do it, and Dr. Michal Eskes from the Weizmann Institute. So what I really want you to focus here is what I say generally. Michal is capable of using dynamic nuclear polarization, putting radicals into the electrolyte solution. And then she can use microwaves and polarize the nuclei on the surface of the coating. And by the distance of the signal she sees, she can say what is the really environment close to the surface or into the, it's not a bulk, it's a 3 nanometer thick, but she could really say what is the difference between. So when I'm looking here, what you see here, this is a more inorganic silicon oxide, and this is more with organic residuals, and the higher intensity here suggests that more close to the outer shell, there are residuals of organic moieties. When you go deeper to the proximity of the inorganic electrode, then you have a more inorganic environment. And this is very desirable for electrolyte solutions in a battery, because now the wetting of the electrode should also be improved if there are organic residuals on the surface. And we could detect it also with the electrochemistry. So if I showed you before that this is the alumina base, when we go to 4C, we do not see improvement. This was 41% improvement when we are coating it with our lithium silicate. Yes, she's doing it. So it's a this is not inoperando battery study. We're just studying the composition of the thin film. So we are following it after process of ALD. So we first coat it, and then we give it to Michal, and she's characterizing she gives us the composition of the coating from the depth. It's a 3 nanometer deep, but this is what she's capable of doing. So it's a post treatment.
I understand that you had better technique, but how to explain the higher capacity coating?
Okay, so this is a very good question. We get it regularly. So one thing with all these materials are highly unstable even at room temperature. And you know that the processing of the battery is involved in exposure to NMP and methylpyrrolidone. We can see that it is reacting spontaneously with any organic solution you put in. So once you started less good with the oxide material when it is not coated. So it is improving the capacity even at the beginning. Another thing we saw, mostly with the zinc related and silicon related, that there is opening of the orifice. So there are clogged On synthesis, you will have some remaining rock salt phases on the surface of the particles, and this is suppressing the capacity. So these are full cells, meaning real battery in a pouch cell, similar to what you have in your cell phones. We have these capabilities of closing cells, and we can see that these are very promising results, more than 80% capacity retention after 200 cycles of a full battery cell. Now, another thing that Michal is capable of doing is really following the mechanistic or the lithium-ion mobility, not only through electrochemistry that I showed you before, which is a very good indication, but yet what we did here, we cycled the battery in a lithium-6, and so in an isotopic lithium environment, enriching the cathode material with lithium-6. And then Michal took it and dipped it in electrolyte solution, and this is done in operando. It's not in operando battery, but you can follow the exchange of lithium-6 from the cathode, and there is a very improved rate for lithium exchange through the thin films of the protected one compared to the uncoated one. So it's supporting very well the kinetics we measure with electrochemistry. So you dip it in a regular electrolyte solution after you enrich it with lithium-6, and you can follow the rate of exchange. So it is significantly improved when we have our coating. Again, that's the evolution of the gaseous phase. This is a CO2 evolution, significantly suppressed after film protection, and the same goes for the cracks formation after 100 cycles inside the battery. These are the high resolution SEM of the protected one versus the unprotected one. How much time do I have? Close to finish. Okay, so one more example is, as it says, it's in 115 in this schedule. 115. This is what it said. I'm fine. So again, instead of introducing just inorganic composition, we can have surface film, which is based on molecular layer deposition. This is an example with ethylene glycol and hydroquinone. Here it was kind of obvious to begin with that the choice of ethylene glycol will be better because the distance between the oxygen at the thin film will be smaller. So the hopping of lithium between the oxygen should be faster. We just used it as a blunt, and we are capable of showing that the surface protection improves the stability. But if you choose a lithium ion conductive surface protection, you have two advantages. One, you improve the stability, and the second one, you also improve the kinetics, so the capacity retention is also significantly improved. So I hope I convinced you today that functional material, even though they degrade through the interface, a scientifically informed choice of thin functional protection layer can fix the interface and significantly improve the long-term stability of the battery. I showed you how we use online electrochemical mass spectrometry as a pathologist for battery degradation pathways, and how manipulation of atomic and molecular layer deposition processes can help get a desired functional thin film. And this is a more cartoon-like summary of the message of my talk. And again, I want to thank my group. This is a COVID time. Online electrochemical mass spec is done by now Professor Rosie. She's now an assistant professor at IIT Varanasi. And the synthesis of the cathode is done by Ayan. He got a position in IMMT. And Dr. She did the molecular layer deposition, and with that, this is a more happy environment of the group, not far away from here. And with that, I'm happy to conclude and to take questions. Thank you.
We know that epitaxy is very important in other scenarios and so on. So this is like magic somehow. It really helps. What's going on at the interface over there? The atomic scale, let's say.
So I maybe the Via de la Rosa or the agony part is not shown in this kind of presentation, but many times when we take surface that is too clean, if I take lithium titanate, it's a good example. it's very hard to grow using atomic layer deposition on this kind of film. So the reaction pathway, which is very nice in cartoons with hydroxyl termination, you either need to first terminate it intentionally with hydroxyls in order to have growth, or you need to try to find a different process. So what I showed you with the silicate is an example. We couldn't coat it with a regular TMA or unless we have the surface reduction. We chose a complex like chemistry. So if there is a transition metal close to the surface, it's not epitaxial growth, it just goes and complexate with the transition metal, and then it grows on the surface of this complex. And we are demonstrating that with molecules that are TD-MAT, like for titanium oxide, and the silicate is with silicium, but it is more like complex or coordination chemistry rather than a click chemistry. And yes, if we want to go epitaxial growth, it's a challenge because the temperature is not where we can demonstrate epitaxial growth.
General question, because I also when I try to make the composition. So the question is how to select coating and how to maybe a way to predict what will be the effect of the coating even before the ALD process. How to select the best precursor for the coating.
Okay, so these are few questions in one question. Okay, so if I want to select the coating of interest, I need to have few parameters. One, the coating should be better to be thermodynamically stable at the voltage of interest. You can follow the works of Ifemo and also Cedar and Pearson, Catherine Pearson. Also, surface stability of a solid electrolyte is very important because if you go to high voltage, the Lipon-like processes will decompose spontaneously to lithium phosphates rather than the Lipon or even lithium phosphide, and then you have insulating layer on the surface of your cathode. This is why we went to lithium silicate because of the thermodynamical stability. Now, not always you can find precursor for doing what you're interested in, but this is one sample. Okay. The second one, you want it to be ionically conductive. So it is not always possible to synthesize a priori ionically conductive, but sometimes at the right voltage, you already know that it will be lithiated and become ionically conductive. So for example, alumina at lower voltages can become lithium aluminate. If you control the conditions, it will become lithium aluminate and then you're good to go. So these are two important guidelines for choosing. And the other thing, you want it to be stable chemically in the relevant electrolyte solution. So if you are working with water, like water in salt, you need to avoid surface films that will go through hydrolysis, for example. And if you are working in organic solvents, you can't really trust all the organic moieties because if they will dissolve and then will shuttle to the anode, you are forming a different problem on another interface. So these are the main guidelines for choosing thin films. And at the end, you hope you can find a precursor.